and welcome to Physics 1, Lab 4, Oscillations. Introduction. The purpose of this experiment was to first perform visual analysis on a spring mass system in a video via tracker, then take that data from the analysis and create a computational model of the energy, and then compare the computational model and visual analysis. The physics principles present in this lab were Newton's second law, or the momentum principle, which states that force is equal to the change in momentum per change in time, or F equals ma, and the energy principle, which states that energy cannot be created or destroyed, and that energy is transferred between forms. The equations used for this lab were Newton's second law, F equals ma, the velocity and position update equations, the period equation, which is 2 pi times the square root of m over k, with m being the mass and k being the spring constant, total energy, which is E initial equals E final, kinetic energy, which is 1/2 mv squared, gravitational potential energy on Earth, which is simply mgh, and spring potential energy, which is 1/2 k length of the stretch squared. Here's a preview of my results. And for the models, we first have the video analysis, which is simply a video of a spring mass system moving in a circular oscillation. Then the data was then calibrated so that the length of the spring was 1 meter, and the mass and spring constant were found from weekly preview video 52, and then the motion of this object was plotted by hand in tracker. The computational model used the energy principle and update equations to accurately plot the motion of the object and produce trend lines for each form of energy present in the system. For the visual analysis, once again, it was hand-plotted points of motion throughout the video. It created a sinusoidal curve to represent motion in both the x and y directions, with the x direction representing a sine curve and the y direction representing a cosine curve. And delta t was then found through just the frames per second of the video, with delta t being 0.95 seconds. For the computational model, once again, all of our constants were found from weekly preview video 52. This is the initial values for length, L hat, and the stretch of the spring, the initial values for all forms of energy in this system, and within the loop over the course of 10 seconds, it's simply stating the initial energies for that time interval for delta t, the force of gravity, which is just mass times gravity, the force of the spring, F net, which is force of gravity plus the force of the spring, the update equations for the mass, then updating the spring position, and then finally updating and plotting our changes in energy. So, for the results, we can see that the spring potential and gravitational potential energy oppose each other, as well as delta K and delta E opposing each other along this flat line. So, what does this mean? This means that the experiment does satisfy the energy principle. As previously seen in the graph, the spring potential and gravitational potential oppose each other equally throughout motion, as well as the kinetic energy and the change in tonal energy also matching each other sinusoidally. These sinusoidal opposites show that no matter the motion, the energy is conserved. What if? The period for both observed motion in the x and y directions is 1.52 seconds. This is found from the period equation, as both y and x directions share the same mass and spring constant, meaning they share the same period. This can also be seen visually from the observed motion graph. Conclusion. This lab showcased the effects of the energy principle and how kinetic, gravitational potential, and spring potential energy work together to make an object move. Thank you for watching.